So we have this basic problem in computing. We want our computers to deal with information like images, audio, video, 3D models and 3D animation, and just simpler stuff like text and numbers. The problem is that if we're going to store such things in a computer, we have to store them in the form of bits. A bit, as you likely know, is simply something that holds one of two states, and we represent these two states as the digits 0 and 1. So for instance, the flag on your mailbox, which goes up and down, can be thought of as a bit. At any moment in time, it's holding one of two states, either up or down, and we could either assign up to be 0 and down to be 1, or the other way around. It's basically arbitrary which we choose. The important part is just that the bit makes a clear distinction between its two states. In computers, the actual physical mechanism we have for representing bits varies from one technology to another. For instance, memory chips use either capacitors or transistors, optical disks use microscopic grooves that are read and written by lasers, and floppy disks and hard drives use charges on a magnetically sensitive surface. A bit really is an abstraction, it's not a tangible thing. Just like, say, a word is an abstract thing distinct from the tangible word written on a piece of paper. So it works out that the key to representing any kind of data as bits is to first use bits to represent numbers. So how do we do this? First, understand the concept of a number system. A number system is a scheme for symbolically and verbally representing quantity. Now, of course, in a sense, you already understand number systems because you already use one. You use what is called decimal. However, understand that decimal is just the number system we've settled upon for historical and largely arbitrary reasons. First, consider what is perhaps the simplest way to express quantity, what is called the unary system, or more commonly, the tally system. In the tally system, you simply make a mark, usually just a line, for each thing that you're counting. So for instance, to represent the quantity 1, you just make one mark. To represent the quantity 2, you would have 2 marks, 3 would be 3 marks, 4 would be 4 marks, 5 would be 5 marks. And notice that by convention, we group the marks into 5 such that every 5th mark is written diagonally through another set of 4. The obvious problem with the tally system, and the reason we don't use it much today, is because it takes up a lot of space to express even moderately large values. For instance, if you wanted to express the quantity 1 million, you would be writing marks for weeks. And even if you finished, the end result would be totally unreadable. Another possible scheme is if we decided to devise a unique symbol for every single possible quantity. One obvious objection to this is that, well, there are an infinite number of quantities, so we couldn't actually do this. The other obvious objection is that even if we stopped at some number, say 1000, it would still mean we would have to learn 1000 unique symbols, and that's just not practical. A much better solution is to use what's called positional notation. Positional notation represents arbitrarily large quantities using a finite set of symbols. The decimal system that you're familiar with, which we also call base 10, is in fact positional notation. It's the positional notation system that uses 10 symbols. The 10 symbols we use in the West are called Arabic numerals. Ironically, in the Arab countries today, they use a different set of numerals that is sometimes called the Indian numerals, sometimes called the East Arabic numerals, as opposed to what we use, which are called the West Arabic numerals. And in India, they use what are called the Devanagari numerals. Whatever you call your set of symbols and whatever they look like, the important idea in positional notation is that they have an established order. The order of our numerals is what you see here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. What this order means is that if we are, say, at 2, and we wish to express the quantity which is 1 higher, then we go to the next symbol in the sequence, we go to 3. And then if we want to express 1 higher than that, we go to the next symbol, which is 4, and then 5, and so on. We don't go from 2 to 7 or 1 or whatever, we stick to the order. The question then is what happens when you get to the last symbol 9? How do you express 1 higher than that quantity? Well, what happens is that we loop back to the first symbol, 9 goes to 0, and we cycle the digit place to the left. So say, to express the quantity 1 higher than 3, 9, the 9 cycles back around to 0, and the digit to its left cycles by 1 from 3 to 4. Well, you may be wondering then, well, what if there isn't a digit to the left when we cycle a 9 to 0? The answer is that when we have any number in positional notation, there's always a digit to the left. There's an infinite number of them, in fact, and they're all set to 0. So say what we express as just 9 can be thought of as 09, or 00000000009. We just usually omit those zeros and leave them implicit. We can't write them all anyway because there's an infinite number of them. So say if you have the quantity represented by the single digit 9, the way you express 1 higher is that the 9 cycles from 9 back down to 0, and then the digit to its left, a 0, cycles up by 1 to 1. And this is the value we call in decimal 10. Note that when you have a series of 9s in the rightmost digit places and you want to express 1 higher, you get a cascading effect. So here, when you express 1 higher than 86999, what happens is that the rightmost 9 cycles from 9 to 0, causing the digit to its left to cycle from 9 to 0, causing the digit to its left to cycle by 1 from 9 to 0, causing the digit to its left, the 6, to cycle by 1 to 7. So 86999 becomes 87000. Understand that English and most other modern human languages presume decimal. We have a name for each of the Arabic numerals, but then when those numerals are put in digit places other than the rightmost one, we have to change how we call them. So for instance, we say 78, we don't say 78. The historical decision to use positional notation was not an arbitrary decision. Positional notation is clearly superior to alternatives. However, the choice to use 10 symbols is just arbitrary. Positional notation works just fine as long as you use at least 2 symbols. So say you could have a base 3 system, a base 17 system, or a base 1065 system, or whatever. The only real guiding logic in this choice is that, well, you obviously wouldn't want a number base that's too big, because that would mean memorizing and using a whole lot of symbols. The decision to use base 10 was likely made simply because humans have 10 fingers and 10 toes, so it seems natural to people to use base 10. However, some civilizations, like the ancient Babylonians, actually used base 12, likely because it fit best with their calendar. So let's look at what happens when we use something other than 10 symbols. The system in which we use 8 symbols is called base 8 or octal. In octal, we still use the Arabic numerals, but we ditch the symbols 8 and 9. And recall the rule is that when we cycle digits, when we get to the last symbol, we cycle back to the first. So we're going to cycle, instead of from 9 to 0, we're going to cycle from 7 to 0, because 7 is the last symbol in octal. So here we have the quantity 7, and we wish to express 1 higher, so the 7 cycles back down to 0, and the digit to its left cycles to 1. So that the quantity which in decimal we call 8, in octal is written as 10. This is confusing because of a lifetime of habit. It's just very difficult to look at 10 and not immediately think 10. So here's what happens when you count side by side in decimal and octal. As you can see, the quantity which we call 12 in decimal is in octal the digits 1, 4. And if we continue counting, you can see here that the quantity which we call 24 in decimal in octal is written as 3, 0. So the way we count in octal is the same way we do so in decimal, it's just that we're using 8 symbols instead of 10. And whereas in decimal we saw this cascading effect when the rightmost digits of a number were 9 and we wish to express 1 higher, in octal you see the same effect when the rightmost digits are 7, because whereas in decimal 9 is the last symbol, in octal 7 is the last symbol. So when we want to express 1 higher than the quantity 317777, we get 320000. Because what happens is at first the rightmost digit cycles by 1, so it cycles from 7, the last digit, back down to 0, the first, causing the digits to its left to do the same in turn, until finally the 1 cycles to 2. Because octal uses the same numerals we use in decimal, we therefore need some way to distinguish a number which is meant to be octal and a number which is meant to be decimal. There are a number of conventions for doing this, but the most common is to precede an octal number with a single 0 digit. So if you see a number written 61, you can just assume it's decimal, but if you see a number written 061, that's meant to indicate to you that it's meant to be octal. To be honest, I don't find this way of designating octal numbers particularly clear. I suppose the idea is that a 0 looks like an O as an octal. But this is just a solution for distinguishing number bases when numbers are written. When I say a number aloud that's not in decimal, I should explicitly state the number base. So instead of saying 61 to mean 61 octal, I should say 61 octal or octal 61. Actually, I shouldn't say 61 octal, I should say 61 octal. The problem with the way that we say numbers in English is that it presumes decimal. For instance, if I say 5,673 octal, this is confusing because it's very difficult to hear those words and not automatically think in terms of decimal. It's much clearer if I remove the natural bias we have in English for decimal by saying just 5673 octal instead. So octal is an example of using positional notation with a base of less than 10, but what about a base greater than 10? One such number base we might use is base 16, also commonly known as hexadecimal or just hex for short. Because hex uses more than 10 symbols, we can't just use the standard Arabic numerals. But rather than contriving new symbols, we just use the same Arabic numerals as we do in decimal, and then we add the first 5 letters of the alphabet. And these letters can be written either uppercase or lowercase, it doesn't matter. So the symbols in hex are in order 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So now because F is the last symbol in the sequence in hex, when we cycle digits, we cycle from F back down to 0. So when we count in hexadecimal, it looks like this. The quantity which we write 10 and call 10 in decimal, in hex is just written A, and it's not until we get to the quantity which we call 16 in decimal that we begin to use more than just one digit. 10 hex is equal to 16 decimal. And here we see the pattern continue. Notice for instance that the quantity 20 hex is equivalent to 32 decimal. When we write numbers in hex, we get the same issue we get in octal, where we may not be able to discern just by looking at the number that it is intended to be written in a number base other than decimal. In hex though, we also get this issue where some hex numbers actually look like words, because a hex number might be made up entirely of the letters A through F. The solution to both these problems is we need some way of denoting a hex number, and a common convention for this is to precede a hex number with 0x, and the x can be either uppercase or lowercase. Here I have it lowercase. And finally, whereas in octal we saw the cascading effect when the rightmost digits were 7s, and in decimal we saw this effect when the rightmost digits are 9s, in hex we get this effect when the rightmost digits are f's. So if we have the quantity A3BFFFFF in hex, and we wish to express one higher, then what happens is first the rightmost f digit cycles by 1, so it cycles back down to 0, causing the f's to its left to cycle to 0 in turn, and then finally causing the b digit to cycle to c. The alternative to decimal, which we really care about, is base 2, also called binary. In base 2, we just use the two symbols 0 and 1. And that there should be the clue that tells you why we care about binary. If we can represent quantities using just two symbols, then we can store quantities as bits. So, because 1 is the last digit in the sequence in binary, when we want to express one higher than 1, we cycle 1 back down to 0, and the digit to its left cycles to 1. And this is what it looks like when we count in binary and decimal side by side. The striking thing here is that in binary, because we're using so few symbols, just 2, we end up using a lot of digit places very quickly, even to represent small quantities. So as you can see, the quantity which we call 8 in decimal, in binary is represented as 1000. We've only gotten to the quantity 8, and already we're using 4 digits. And as you can see, the quantity which is 16 in decimal, we call 10000 in binary. We're already using 5 digits by the time we get to 16. To distinguish binary numbers from decimal numbers, we typically just stick a b at the end of the number, either uppercase or lowercase, though I generally find lowercase is more distinctive because it doesn't look like an 8. Now, whereas in decimal we saw the cascading effect when the rightmost digits were 9s, and in octal we saw the effect when the rightmost digits were 7s, and in hex we saw the effect when the rightmost digits were f's, in binary, 1 is the last digit, so we see this cascading effect when the rightmost digits are 1s. So here, for example, if we have the quantity 10101111 binary, and we wish to express one higher, well, we get 10110000 binary. Because we start with the rightmost digit and cycle it by 1, so it goes from 1 to 0, causing the digit to its left to go from 1 to 0, and so forth until we hit the first 0, and that cycles to 1. If you have a quantity expressed in one number base, how do you find how that quantity is expressed in another number base? To understand this, we first need to consider a different way of thinking about positional notation. Say I have this decimal number 36,259. This is equivalent to 30,000 plus 6,000 plus 200 plus 50 plus 9. In other words, we can think of the whole as a sum of individual digit places. We can go a step further and say that this in turn is equal to the quantity 3 times 10,000 plus 6 times 1,000 plus 2 times 100 plus 5 times 10 plus 9 times 1. And we can go one step further and say that this is equivalent to 3 times 10 to the 4th plus 6 times 10 to the 3rd plus 2 times 10 to the 2nd plus 5 times 10 to the 1st plus 9 times 10 to the 0th power. Anything to the 0th power, recall, is equal to 1. So 10 to the 0th is 1. So what we've done here is in fact derived the usual definition that mathematicians give to positional notation. In this definition, each digit place represents that digit multiplied times an increasing power of the number base. So in decimal, because our number base is 10, we start on the right with 10 to the 0th, which is 1, then 10 to the 1st, which is 10, and then 10 to the 2nd, which is 100, 10 to the 3rd, 10 to the 4th, and so on. So using this definition, let's look at an example of converting from octal to decimal. Say we wish to convert the octal number 3675 into decimal. Well, first we break it into the component digits, so we have octal 3000 plus octal 600 plus octal 70 plus octal 5. And then we go one step further by factoring out the actual digit. So say octal 600 is equivalent to octal 6 times octal 100, and then the next step is to express these in terms of powers of the number base. And of course in octal, 8 is written as 10. In fact, in all number bases, the number base is always written 10. In binary, 2 is 10. In hex, 16 is 10, and so forth. This is not a coincidence. But in any case, now we've broken everything into very small numbers which we can just easily convert in our heads to decimal. So 3, 6, 7, and 5 all in octal are obviously in decimal just the same thing. And 10 in octal is 8 in decimal. So now we have this quantity expressed entirely in terms of decimal, and we just need to do the arithmetic. So first we do the powers, and then we do the multiplication, and then we just sum it all together. And the sum we get is 2081. So octal 3675 is equal to decimal 2081. So what if we want to go the other way, from decimal to octal? Well, we can use the exact same technique. We break our big number up into small enough terms that we can directly convert them, and then we just do the arithmetic to put it all back together. So let's say we want to convert decimal 36,256 into octal. Well, first we break it up so that we're multiplying each digit times a power of the number base, in this case 10. And now that we have everything in very small decimal numbers, we can simply directly convert them into octal. So now we have everything in terms of octal, and we can do our arithmetic. The problem is that we're going to be doing the arithmetic in octal. It's of course perfectly doable, but it just tends to be confusing because you're not used to doing it. So just take my word for it that this is what you get when you expand the powers. This is what you get when you do the multiplication, and when you sum it all together, you get octal 106640. That is what is equivalent to decimal 36,256. Again, this technique works for all conversions. The only trouble is that when you do a conversion to some number base other than decimal, the arithmetic tends to be tricky because you're not used to doing arithmetic in that number base. When converting from binary to decimal, again we can use the very same technique, but as you'll see, it actually works out to be the simplest kind of conversion to do mentally. So say we wish to convert binary 10101 into decimal. As usual, we break it into the component digits multiplied by some power of the number base. We then expand the powers and do our arithmetic, first the multiplication, and then we sum everything together to get 21. So 21 decimal is equivalent to binary 10101. You may have noticed that what made this conversion so easy is that we ended up just summing together powers of 2, and that's all we will ever do. We never end up doing any even moderately difficult multiplication because we always end up just multiplying by either 1 or 0. So for example, say we wish to convert 10101101 binary. To do this, all we have to do is memorize the power of 2 that corresponds to the digit places with 1s in them. So starting from the right, the powers of 2 go 1, 2, 4, 8, 16, 32, 64, 128. But we just take the powers of 2 corresponding to the digits with 1s in them, and we sum them together, and we get 173. 173 decimal is equivalent to 10101101 binary. So it works out that as a programmer, it's a good idea to memorize the powers of 2 up to about 2 to the 20th. 2 to the 20th is a good stopping point because beyond that the numbers get pretty big, and so they get a bit unwieldy to compute mentally. This unique aspect of binary, that each digit represents the presence of a power of 2 or just its absence, this suggests there's another way of doing conversions from decimal to binary other than using the standard technique. In this alternative technique, we take our decimal number and we find the biggest power of 2 that fits in it. That power of 2 corresponds to a 1 digit in the equivalent binary number. So for instance, if the biggest power of 2 is 8, then that means that the leftmost 1 in the binary equivalent is the 4th digit from the right. Once you find this digit, you then subtract out the power of 2 from the decimal number, and then with the result, you repeat the process. You try and find the biggest power of 2 in that number. This process repeats until finally you subtract it down to 0. There are no more digits to find at that point. Let's see how this plays out. Let's say we have the decimal number 35,872. Well, if I'm familiar with the powers of 2, I can quickly see that the biggest power of 2 that fits in this number is 2 to the 15th, 32,768. This tells me that in the binary equivalent of this decimal number, the leftmost digit place with a 1 in it is the digit place corresponding to 2 to the 15th, and that's the 16th digit place from the right. At this point, that's all I know. I don't know what the remaining digits are going to be. They might be zeros or ones. We will find out. So my next step is to subtract out 2 to the 15th from my decimal number, leaving me with 3,104. The biggest power of 2 to fit into 3,104 is 2 to the 11th, or 2,048. This tells me that the next leftmost digit place with a 1 in it is the digit place corresponding to 2 to the 11th, which is the 12th digit place from the right. I then subtract out 2 to the 11th, leaving me with 1,056, into which the biggest power of 2 that fits is 2 to the 10th, or 1,024. This tells me that the next leftmost digit place with a 1 in it is the one that corresponds to 2 to the 10th, which is the 11th digit place from the right. I then subtract out 2 to the 10th, leaving me with 32, and of course the biggest power of 2 that fits into 32 is 32 itself, 2 to the 5th, which tells me that the last digit place with a 1 in it is the one corresponding to 2 to the 5th, which is the 6th digit place from the right. If I subtract out 32 from 32, I'm of course left with a 0. This tells me that I'm done. I've found all the digit places that have 1s in them, so I know that all the remaining ones just have 0s. I briefly explained why we care about binary. As I'll expound upon in a moment, it's how we can store numbers as bits. But you may be wondering, why did I bother introducing hex and octal? Well, aside from helping to illustrate the concept of an alternative number base, something other than 10, hex and octal have a special relationship with binary, and this is because 2, 8, and 16 are all powers of 2. It works out that when one number base is a power of the other, such as 2 and 8, 8 is a power of 2, conversions between those two number bases can be done without doing any arithmetic at all. So as I'm about to show you, converting between octal and binary and converting between hex and binary is extremely easy. You can do it in your head, no problem whatsoever. This helps mitigate a practical problem when dealing with binary, and that is that binary numbers are quite verbose. As we saw, when we expressed even small quantities in binary, we started using a lot of digits very quickly. This makes it very inconvenient if we want to, say, write a binary number down on a piece of paper. The solution is to not write out binary numbers at all. We can simply use octal and hex in binary's place. Because the mental conversion process is so simple, anyone looking at the octal or hex who wants to know what the binary equivalent is can easily find it out. So let's say we wish to convert from octal to binary, or vice versa. All we need to do is memorize the 3 binary digits that correspond to each octal digit. The octal digit 5, for instance, is equivalent to the binary digits 101. The octal digit 2 is equivalent to the binary digits 010, and so forth. So if I have the octal number 3673, I can convert it to binary if I simply know what the binary equivalent of each digit is. When we consult our chart, we can see that octal 3 is equivalent to the digits 011, octal 6 is equivalent to the binary digits 110, and octal 7 is equivalent to the binary digits 111. If I plug these facts together, I can quickly see that octal 3673 is equivalent to binary 11110, 111011. And I can just as easily go the other way. If I have binary 11010101110, then I take these digits and I group them into threes, starting from the right, and then I simply directly translate each group of 3 binary digits into its corresponding octal digit. Because 16 is a power of 2, the same idea works with conversions between hex and binary. The only difference is that each hex digit corresponds to 4 binary digits. So if I simply memorize the binary equivalents of each hex digit, I can immediately see that hex 7E9 corresponds to binary 11111101001. And I can just as immediately see that binary 1100101101 corresponds to hex 32D. Before finally explaining how exactly bits are used to represent numbers, let me explicitly establish a basic philosophical point, and that is that all meaning relies upon agreement. For instance, the fact that all English speakers picture approximately the same thing when they hear the word dog relies upon a natural and informal agreement that that is what the word dog refers to. The implication this has in computing is that when a program writes data to some place in memory, the only way that data has any meaning is if the thing which is going to read the data interprets the data consistently with the writer's intention. For instance, imagine I write 16 consecutive digits on a piece of paper. If it's my intention that the first 7 digits are a 7-digit phone number, while the remaining 9 digits are a social security number, that meaning is not inherent in the numbers themselves. If I, the writer of these numbers, come back a week later to read them, but I've forgotten what I intended when I did so, then the meaning is lost. For instance, if I reverse the order and read the first digits as being a social security number and the last digits being a phone number, then I'm going to be misinterpreting the data. Computer memory has very much this same problem. Memory is just a sequence of bits. If I store something in memory, I can't label it with an indicator of what it's meant to be. The bits just are what they are. So for any data I write, I have to be careful to remember where I put it and what it's meant to mean. So let's finally look at how exactly we represent numbers as bits. First we'll start with integers. An integer, remember, is just the fancy term basically for whole numbers. That is, numbers without any kind of fractional component. So examples are 5,878, 0, -87, or 234. When we represent integers as bits, we do so in 2 basic forms, either signed or unsigned. A signed representation can represent both positive and negative integers, but an unsigned representation can only represent positive integers. An unsigned representation of a number is straightforward. All we do to represent a decimal number is to store it as its binary equivalent. So say we represent decimal 3 as 11 because that's the binary equivalent. An important thing to know is, given however many bits you have, how many different unsigned values can you represent? The answer is that if you have n bits, then you can represent 2 to the n unique values. This makes sense because if you have 1 bit, then you can only represent 2 possible values, 0 or 1, but then if you add 1 more bit, you are effectively doubling the number of values, from 2 to 4. If you add another bit, you're doubling again to 8. And in fact, every time you add 1 more bit, you're doubling the number of possible values. Another important thing to know is, given n number of bits, what is the range of unsigned values we can represent? The answer is that if we have n bits, the lowest value is always 0, whereas the highest value is 2 to the nth minus 1. For instance, if I have 6 bits, that means I can represent 2 to the 6th unique values. 2 to the 6th is 64, so I have 64 different values, but 0 itself is one of those values. So the maximum value is 1 less than 64, it's 63. To represent signed integers, there are a number of different ways of doing it. The most obvious way is to use what's called a sign bit, which is exactly what it sounds like. It's where we take a single bit in our number and reserve it to indicate the sign. So for instance, if I have 8 bits in which to represent a signed integer, and I wish to represent positive 3, it would look like this. But negative 3 would look like this. We simply use the most significant bit as a flag, and when it's set to 1, that indicates the number is negative. An alternative is called 1's complement. In 1's complement, positive integers look the same, but to get the negative of a positive, we simply flip all of the bits. It's still actually the case that the most significant bit indicates the sign, but as you can see, it's more than this that separates a negative number from its absolute value. A slight variation on 1's complement is called 2's complement. Like in 1's complement, 2's complement negates a number by flipping all of the bits, but then we perform the additional step of adding 1. This in fact works both ways, so if I want to negate negative 3, that is if I want to get positive 3, I flip all of the bits and then I add 1. Again, in this form, like the others, the most significant bit still effectively indicates the sign of the number. So if the most significant bit is 1, then the number is negative, but if it's 0, then it's positive. You're probably wondering why the hell would anyone want to use 1's complement or 2's complement when they could just use a sign bit. The reason, it turns out, is that processors can do arithmetic upon numbers in 2's complement form more efficiently than they can upon numbers that use a sign bit. So 2's complement is the form most often actually used, but there's one more form called XSN. The idea in XSN is that we pick some arbitrary positive integer to represent 0. Everything above this number will be positive, whereas everything below it will be negative. So for instance, if I want to represent positive 3 in XS8, I represent it as 11, because 11 is 8 plus 3. But if I wish to represent negative 3 in XS8, I represent it as 5, because 5 is 8 minus 3. Notice that in XS form, we don't have a sign bit. For another example, let's say we wish to represent positive 3 in XS42. Well then, we represent it as 45, because 45 is 42 plus 3. Conversely, to represent negative 3 in XS42, we represent it as 39, because 39 is 42 minus 3. Note that the interesting thing about XS form is that how large our positive range and how large our negative range is depends on precisely which number we choose for n. If we choose XS8, then our negative range is going to go from -1 to -7, whereas if we choose XS42, our negative range is going to go from -1 to -41. For the other forms, the range simply depends on how many bits we're using. So say for an 8-bit number, if we're using just a sign bit or we're using 1's complement, then the range is going to be -127 to +127. This seems odd until you realize that in these two forms, we have both a positive 0 and a negative 0. In 2's complement form, however, we only have one representation of 0, and we actually have one more value in the negative range than we do in the positive. So the range is -128 to +127. That's all there is to know about representing integers, but what about rational numbers? A rational number, recall, is a number that's expressed as the ratio between two integers, a numerator and a denominator. The rationals are actually a superset of the integers, that is, integers themselves are rational. For instance, the integer 3 can be expressed as the ratio 3/1. Integers and rationals differ in one important property. Both integers and rationals stretch off into positive infinity and negative infinity, but between any two rational numbers, there's an infinite number of other rational numbers. This is not the case with integers. Between any two integers, there's a finite number of integers. The implication of this is that when we say you can represent this range of rational numbers given this number of bits, we don't mean you can represent every possible rational number in that range. because you simply can't represent an infinite number of values unless you have an infinite number of bits, which of course we never do. Rational numbers are often not expressed as ratios, but rather as an integer component and a fractional component separated by what's called a radix point. This is called radix point notation. For instance, the ratio 3/4 is represented in radix point notation as 0.75. To understand radix point notation, we need to revise our definition of positional notation. Let's say we have the number 36.259. We can represent this as the sum of the individual digit places like so, which in turn is equivalent to the sum of each digit place multiplied times some power of 10, the number base. What's new here though is that the digit places to the right of the radix point have negative exponents, whereas the digits to the left of the radix point are multiplied by the number base raised to an exponent that increases starting from 0. The digits to the right of the radix point are multiplied by the number base raised to an exponent that decreases starting from -1. For instance, here's octal 62.732 and here's binary 10.111. It's important to realize that some rational numbers are finite whereas others are not. A finite rational number is a rational number which can be represented in radix point notation using a finite number of digits. For instance, 3/4 can be represented as 0.75, -7/1 is finite because it can be represented simply as -7, and 138/20 is finite because it can be represented as simply 6.9. However, 1/3 is not finite because it would take in fact an infinite number of 3's to the right of the radix point to fully represent. If we wrote 0.33333333, that would just be an approximation. Now in fact, the way it works out is that all rational numbers are finite in some number bases, but then not finite in other number bases. For instance, 1/3, when we express this in radix point notation in decimal in base 10, it's not finite, but if we were to express it in base 3, it would be finite. In base 3, 1/3 would be represented as simply 0.1. Conversely, the ratio 3/4 is finite in decimal, but in base 3 it is not. In fact, there's a relatively simple formula we can use to determine whether a ratio is finite in some particular number base. The rule is that if the denominator of a ratio is equal to the product of the factors that make up the number base, each multiplied times some exponent, then that ratio is finite in that number base. So for instance, decimal is base 10, and 10 is made up of the factors 2 and 5. So if a ratio has a denominator which is equal to 2 raised to some power a multiplied by 5 raised to some power b, where both a and b are positive, or 0, then that ratio is finite in decimal. You may have noticed that we didn't include 10 itself as a factor of 10. If instead of 2 to the power a times 5 to the power b, instead we had 2 to the power a times 5 to the power b times 10 to the power c, that would just be redundant. It would be exactly the same, because any exponent of 10 can be produced by 2 raised to some power multiplied by 5 raised to some power. For instance, 10 to the second power is equivalent to 2 to the second power multiplied by 5 to the second power. So then it works out that when a ratio has a denominator which is equal to 2 raised to some power, then that ratio is finite in octal, hex, and binary. This is because octal is base 8, and 8 has the factors 2, 4, and 8, but 4 is 2 to the second, and 8 is 2 to the third, so those are redundant. And similarly, hex is base 16. 16 has the factors 2, 4, 8, and 16, but 4, 8, and 16 are all exponents of 2. And lastly, binary is base 2, and base 2 has just the factor 2. The interesting conclusions we should draw from these formulas are these. First, all ratios which are finite in binary are also finite in decimal. But only some ratios which are finite in decimal are also finite in binary. The most straightforward way to represent a rational number as bits is to do so as two separate integers, one for the numerator, one for the denominator. So say this is what it would look like if you wish to represent 3 over 4 using 8 bits for the numerator and 8 bits for the denominator. And this is how you would represent negative 7 over 13, again if you were to use 8 bits for the numerator and 8 bits for the denominator. This scheme is perfectly workable. The only trouble is that it is relatively costly, performance-wise, to do arithmetic upon rationals in this form. A more performant alternative is to use what is basically the computing equivalent of radix point notation, which we call fixed point. In fixed point, we reserve some number of bits to represent the integer component, that is, the digits to the left of the radix point, and we reserve some number of bits to represent the fractional component, the digits to the right of the radix point. So for instance, the ratio 57 over 8, when expressed as binary in radix point, is 111.001. If we use 8 bits to represent the integer component and 8 bits to represent the fraction component, then this is how we would represent it in fixed point. While fixed point makes arithmetic more efficient compared to when we simply represent rationals as two integers, we just established that many ratios aren't finite when expressed as binary in radix point notation. In fact, many commonly occurring ratios, such as 1 over 10 or 1 over 9, or actually any ratio in which the denominator is not a power of 2, those values cannot be expressed in binary radix point, so they can't be expressed in fixed point. The best we can do is approximate those values. This is not to say that the two integers approach is perfect. We're always dealing with a finite number of bits, so there are always values which we can't represent. The difference is that the values we can't represent in fixed point tend to be more surprising if you're not cognizant of this issue of finite rationals. You may recall from one or another science class that you've taken what's called scientific notation or engineering notation. In scientific notation, recall, we take a radix point number as the product of what's called the mantissa or significand and the number base raised to some power. The exponent should be whatever is required to make the significand only have one digit to the left of the radix point. So for instance, 362.354 expressed in scientific notation has a significand of 3.62354 multiplied by 10 raised to the second power. Because when you multiply a number by its number base raised to the second power, it's the same as moving the radix point 2 places over to the right. Conversely, when you multiply a number by its number base raised to a negative power, you're effectively moving the radix point to the left by that number of places. So 0.00736234 expressed in scientific notation is 7.36234 multiplied by 10 raised to the negative third, because that effectively would move the radix point 3 places over to the left. In computing, we use an analog of scientific notation, which we call floating point. In floating point, we represent a rational number as a significand and an exponent, where the significand is represented in binary, and the exponent is the power to which we are raising 2. So let's say we wish to represent 21 over 2 in floating point. 21 over 2 expressed as binary in radix point is 1010.1. Expressed as a significand and an exponent, this becomes 1.0101 multiplied by 2 to the third. So assuming we are using 8 bits for the significand and 8 bits for the exponent, it would look like this. The significand gets transcribed into its bits, whereas the exponent is expressed simply as an integer. As a final exercise, let's try and take this number and put it into floating point. First, we need to express this in binary. The integer 6 is made up of the powers of 2, 2, and 4, so we know in binary it's 110. To convert the fractional component, it's actually easiest if we first express it in its rational form. So 0.75 is equal to 3 over 4. 3 over 4 is the sum of the powers of 2, 1 over 2, and 1 over 4, which are 2 to the negative 1 and 2 to the negative 2. So the digits to the right of the radix point are 1 and 1. Expressed as a significand and exponent, this is 1.1011 multiplied by 2 raised to the second power. So our significand represented in 8 bits is 11011000, and our exponent represented in 8 bits is simply the integer 2. The way I've presented floating point is a workable scheme, but is not the way floating point is actually done in practice. The IEEE is an international standards body, and it prescribes a few standard floating point formats. For instance, there is a 32-bit IEEE floating point standard that prescribes when you are using 32 bits to represent a floating point number, you should use this number of bits to represent the significand and this number of bits to represent the exponent. Similarly, there's a 64-bit standard and an 80-bit standard. These standards also introduce a few special features I didn't discuss. Namely, the standards include a way of representing special values, such as positive infinity and negative infinity. I won't go into details here. If you're interested, look at Wikipedia.